Hi everyone, in this video we will see AHB protocol, which stands for Advanced High Performance Bus. So AHB is a part of AMBA family of protocols developed for communication between different components inside a system on chip or SoC. It is designed for high performance communication between components such as processor, memories, DMA, controller, and other high speed peripherals. AHB supports features such as pipeline transfer, burst transfer, and multiple bus musters. One of the important concepts in AHB is that the address phase and the data phase can overlap, which helps to improve performance. In this tutorial, we will understand how AHB communication works, its important signals, pipelining, transfers, responses, and burst operations. To understand how HB communication works, let's first understand the master and slave. An AHB master is a component that initiates a transfer. It starts the communication by providing an address and control information, and it can either write data to or read data from another component. An AHB slave is a component that responds to that particular transfer. For a write operation, the slave receives and stores the data. For read operation, the slave provides the request data back to the master. For example, a processor or DMA controller can act as an AHB master, while a memory or peripheral can act as an AHB slave. So in simple terms, the master initiates the transfer and the slave responds to that particular transfer. Now let's understand the basic architecture of AHB. In an AHB based system, there can be multiple master and multiple slaves connected through the AHB bus. Since multiple masters may want to use the bus, the arbiter decides which master gets access to the bus. The selected master then starts the transfer by sending the address, control information, and write data when required. Then a decoder uses the address to determine which slave should respond to the transfer. The selected slave then either accepts write data or provide the read data back to the master. So the basic flow is like master, arbiter, AHB bus, decoder, which can select the slave. In short, the arbiter controls which master can use the bus, while the decoder determines which slave should respond. Now let's understand one of the most important concepts in AHB, the address phase and data phase. Every AHB transfer is divided into two phases. During the address phase, the master provides the address and control information of the transfer. Important signals include HADDR, HWRITE, and HTRANS, which we will discuss later. During the data phase, the actual data is transferred. For a write transfer, the master sends data using HWDATA. For a read transfer, the selected slave returns data using HRDATA. The important point is that in AHB, this phase can overlap. While the data for one transfer is being transferred, the address and the control information for the next transfer can already be sent. This overlapping of address and data phase is called pipelining, and it helps AHB achieve better performance. Now let's look more closely at AHB pipelining. In a normal transfer, you might think that the system must complete one transfer before starting the next one, but AHB works differently. While the data phase of the current transfer is taking place, the master can already send the address and control information for the next transfer. For example, while transfer 1 is transferring its data, the data and the control information for the transfer 2 can already be present on the bus. Then during the data phase of transfer 2, the address phase of the transfer 3 can begin. This overlapping continues from one transfer to next, keeping the bus busy and improving the overall performance. This is the basic idea behind AHB pipelining. Now that we understand the basic AHB transfer and pipelining, let's look at the important signal used in AHB communication. Each address carries the address of the transfer. Each write indicates the direction of the transfer. A value of 1 means a write transfer, while 0 means a read transfer. Each trans indicates the type of transfer. We'll understand its different value in the next scene. For write transfer, HWDATA carries the data from master to slave. For read transfer, HRDATA carries the data from the slave back to the master. This signals from the basic communication between the AHB master and slave. Before moving to next signals, let's understand what a burst transfer is. A burst transfer means transferring multiple data values in a sequence as part of one continuous operation. For example, instead of treating four data transfer as completely separate operations, AHB can transfer data 1, data 2, data 3 and data 4 as a part of bursts. This allows multiple transfer to be performed continuously and efficiently. Now let's understand one more signal, HTRANS, which indicates the type of transfer on the AHB bus. HTRANS can have four different values: ideal, busy, non-sec and sec. Ideal means that no transfer is taking place. Busy means that the master is temporarily not transferring data, but it want to keep the control of the bus during a burst. Non-sec indicates the first transfer of a burst or a single transfer that is not part of a sequence. Sec indicates the remaining transfer of a burst where the transfer follows the previous address in sequence. For example, a 4-bit burst normally starts with non-sec followed by sec, sec and sec. So HTRANS tells us that whether the bus is ideal, temporarily busy, starting a new transfer or continue a sequential burst. Before moving to next signals, there is one more important difference between AHB and the AXI protocol, which we have discussed in the previous video. In AXI, communication is divided into separate and independent channels for address and data and response transfers, right? So in AHB, the AHB does not use separate independent channels like AXI. Instead, AHB uses a shared bus interface where signals such as HADDR, HTRANS, HWRITE, HWDATA, HRDATA, HREADY, and HRESPONSE are used for communication. AHB organizes each transfer using an address phase and data phase. So unlike AXI, AHB communication is based on a shared bus with pipelined address and data phase rather than the multiple independent channels. Now let's understand HREADY signal, which tells us whether an AHB transfer can continue or need to wait. When HREADY is 1, the current transfer is completed successfully and the bus can move forward with the next transfer. When HREADY is 0, the transfer is not completed yet, so the master must wait. This happens when the selected slave needs additional time to complete the transfer, for example when accessing a slower memory or peripheral. During this time, the slave effectively insert a wait state by keeping HREADY low. Once the slave is ready, HREADY goes back to 1 and the transfer can continue. So simply HREADY 1 means ready to continue, while HREADY 0 means wait. Now let's understand HRESP, which tells masters the result of a completed transfer. In the basic AHB interface, HRESP can indicate two responses, OK and error. OK means the transfer completed successfully. Error means that the transfer could not be completed successfully. For example, an error response can occur if the slip cannot support the requested access. So while HREADY tells us when a transfer can complete, and HRESP tells us whether the completed transfer was successfully or result in an error. In simple terms, HREADY is timing and completion, while the HRESP is the result of transfer. Now let's put everything together and see how a complete AHB write transfer works. First, the master places the address and control information on the bus. Signals such as HADDR, HWRITE and HTRANS describe the transfer. Since it is a write transfer, each write is set to high. In the following data phase, the master sends the write data using HWDATA. The selected slave processes the transfer. If needs more time, it will keep HREADY low and insert a wait state. Once the transfer is ready to complete, HREADY is high and HRESP indicates whether the transfer completed successfully or result in an error. So the overall flow is like address and control, then write data, and then wait if needed, and then HREADY plus HRESP, and then finally transfer will complete. We already know that a burst transfer moves multiple data values in a sequence. Now let's understand each burst signal, which tells us what type of burst is being used. Each burst can indicate whether the transfer is a single transfer or a part of a burst of multiple transfer. For example, AHB supports single transfer as well as burst with a fixed number of transfers such as 4-bit, 8-bit and 16-bit burst. It can also support undefined length burst, whether the number of transfer is not fixed in advance. So each burst tells the slave the burst type and the number of transfer associated with that burst. Now let's understand H size, which tells us the size of each data transfer in AHB. H size specifies how many bytes are transferred in a single transfer. For example, AHB can perform 8-bit, 16-bit, 32-bit or 64-bit and larger transfers depending on the implementation. So if the transfer size is 8 bits, 1 byte of the data is transferred. If it is 32-bit, then 4 bytes of the data are transferred. SS is especially important during the burst transfer because it helps determine how the address moves from one transfer to next. For example, with a 32-bit transfer, the address normally moves forward by 4 byte of the next transfer. In simple terms, A size tells us the amount of data transferred in one bit. Now that we understand the edge size, let's see how it affects the address used for a transfer. In AHB, the address should normally be aligned with the transfer size. For example, an 8-bit transfer can start at any byte address. A 16-bit transfer is normally aligned to a 2-byte boundary such as 1000 or it should 1002 or 1004. A 32-bit transfer is normally aligned to a 4-byte boundary such as 1000 or 1004 or 1008. Similarly, a 64 transfer is normally aligned to a 8-byte boundary. This alignment helps ensure that the data transfer matches the size specified by a size. In simple terms, the larger the transfer size, the larger the address boundary it must align with. Now let's see how the address changes during a burst transfer. In an incrementing burst, the address moves forward after each transfer according to the transfer size. For example, with a 32-bit transfer, each transfer is 4 byte. So the address can be moved like this: 1000, and it will move to 1004 and then 1008 and then 100C. AHB also supports wrapping burst. In a wrapping burst, the address increments normally, but when it reaches a defined boundary, it wraps back to the beginning of that address range. This is useful when accessing data within a fixed size memory block. So incrementing verse keeps moving the address forward while wrapping verse returns the address to the beginning after reaching the boundary. Now let's see how a complete AHB read transfer works. First, master places an address and control information on the bus. Signals such as H address, H write and H trans describe the transfer. Since this is a read transfer, H write is set to 0. In the following data phase, the selected slave sends the requested data back to the master using HRDATA. If the slave needs additional time, it can keep HREADY low and insert a wait state. Once the data is ready, HREADY goes high and HRESP indicates whether the transfer completed successfully or resulted in an error. So the overall flow is like address and control, and then read data, and then wait if needed, then HREADY plus HRESP, and then finally transfer will complete. Before we finish, let's revisit one of the most important features of the AHB: pipelining. In AHB, the address and control phase of the next transfer can overlap with the data phase of the current transfer. For example, while the slave is providing the data for transfer 1, the master can already place the address and control information of transfer 2 on the bus. This overlap improves bus efficiency because the bus does not need to wait for the for one transfer to completely finish before preparing the next one. So in a pipeline AHB transfer, the address phase of the one transfer and the data phase of the previous transfer happen at the same time. This pipelining is one of the key features that allows AHB to achieve efficient and high performance data transfer. Let's quickly recap what we learned about AMBA AHB protocol till now. We learned how the master and slave communicate, how each transfer uses an address phase and data phase, and how these phases can overlap through pipelining. We also covered important signals such as HADDR, HWRITE, HTRANS, HWDATA, HRDATA, HREADY, and HRESP. Then we looked at the burst transfer, including HBURST, HSIZE incrementing burst, and wrapping burst. Finally, we saw complete AHB write and complete read transfers and how pipelining improves bus efficiency. So AHB is a high performance pipelined bus protocol designed for efficient communication between master, slaves, memory and peripherals. I hope this gave you a clear understanding of how AHB works. Thanks for watching. If you like this video, please subscribe my channel and comment below if you have any queries.